Okay, so there is a relationship among those three different, three different quantities there. And we'll take a look at, this is one of the applications I love about YouTube, and you can actually watch a YouTube video. So let's watch that video together. I hope we have sound. Oh yeah, we do.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves, which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billions of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.
So that's a summary of the waves that we've been talking about, electromagnetic radiation. And there's a lot more videos about electromagnetic radiation on YouTube. So while you're using the YouTube, probably want to spend a little bit more time studying chemistry there. So we want to summarize the relationship that you see in that video there. It talks about the relationship among the three quantities there. This is the first. Remember, I said there are three equations to remember for this part of the lecture there. And this is the first equation. Relationship among these three quantities there. Speed of light equals to the wavelength times frequency. And speed of light is a constant. Okay. Now, speed of light is constant. These two numbers multiply by one another, you end up with a constant. That indicates that there's a relationship between the wavelength and the frequency. They're inversely proportional. One is larger, the other is going to be smaller. You multiply the wavelength and the frequency there, you end up with a constant speed of light. Okay, so this is the equation where I wrote it differently on this one. I put the C on one side, on the left side instead of the right side there. And C is 2.998 times 10 to the 8th meters per second, or more than often you see in the textbook there, 3.00 times 10 to the 8th meters per second. Okay, so using that equation, one type of calculation that we need you to be able to do here is that if we know the wavelength of a particular radiation, 532 nanometer, and we ask you to calculate the frequency. Now, if the wavelength is given, then frequency times wavelength gives you the constant. So plug in the number in this equation there, 532 times the frequency equals to 2.998 times 10 to the 8 meters per second. One thing you have to pay attention to is the unit of the wavelength. When you are talking about the electromagnetic radiation, you're talking about the units in a much smaller quantity, meaning, say here, the speed of light is in meters per second. You cannot plug in 532 because 532 is in nanometer. You have to convert nanometer into meters, so meter will cancel out on both sides of the equation, leaving you with 1 over s, 1 over a second, which is hertz. Okay, so when you do the calculation there, in this case, we have 532 times 10 to the, well, we just use 532 instead of 5.32. Okay. This is in nanometer. Each meter is 10 to the 9th nanometer. Now, that brings up a topic about the first quiz that you turn in there. And when we ask you to convert nanometer into meters or meters into nanometers there, and many people end up with the wrong answer because they put in 1 nanometer equals to 10 to the 9th